So the last colligative property is osmotic pressure. The osmotic pressure is changed. And before you can understand osmotic pressure, we have to talk about what is osmosis. It's not something we commonly talk about it. Maybe I've heard about it in biology somewhere. But anyway, if we have a semi-permeable membrane, so that's what we see right here, a semi-permeable membrane. A semi-permeable membrane is one that allows some materials to flow through, but keeps others from passing through. So you can see here that the water molecules are small enough to pass through. However, these glucose molecules will get stuck on one side. And so you only have flow. You can have flow in both directions for the water, but glucose stays where it is. So what's going to happen? Osmosis takes place. So let's go to the next slide. So if we have a semi-permeable membrane right here on our, and notice that here I have pure solvent on this side, here I have a solution, so maybe some sugar is in the water or something. Well, it's not going to stay like this. So, natural disorder will try to dilute this down. Because they're not the same, it's going to try to dilute it down. So because these bigger molecules can't come through, they all have to stay on the same side, but more of the water molecules are going to come through to try to dilute this side down, the solution side down. So notice that what's happened here over time is that the right side has gone up and this side has come down from where it was. So now, osmotic pressure then is the amount of pressure that you would have to push on this to get it back to where it was. So that's what, okay, so again, osmosis happens through a semi-permeable membrane where the water flows to try to equalize concentrations on both sides of the membrane. Diffusion drives the transfer of solvent molecules, and that's called osmosis. And then in order to either stop this from happening, so not allowing it to happen, the amount of pressure you would have to put on this side to stop it from happening, or another way to think of it is how much pressure would you have to push on this to get it back to where it was. So it's kind of either way. It's called the osmotic pressure. The more concentrated the solution, the higher the pressure is going to have to be, the more you're going to have to push on it to stop it from happening. And this is, if you've ever heard of reverse osmosis filter, that's exactly what's happening. Is you're pushing, it's opposing osmosis. Osmosis naturally flows to the right, but it's actually pushing the water through a membrane the opposite way in the reverse order. So obviously you have to put energy in to try to filter out all the contaminants. So that's just a little aside there, because you probably heard of that before. Okay, so again, osmotic pressure is the colligative property equal to the pressure that when applied to the solution just stops osmosis from happening. So as long as in osmotic pressure is given the symbol pi, it's the capital pi, so it does not mean 3.14, it's just the Greek symbol pi, which is the capital pi, which you see here. So osmotic pressure is the amount of pressure required to stop osmosis from happening. Obviously, the more concentrated the solution is, the larger osmotic pressure is. So that's why it's a colligative property, because the more concentrated it is, the higher the pressure is. So why is that important? It's important, which we'll see on the next slide, because your blood cells, any body cell, the cells are semi-permeable, meaning that they let some molecules in but not others. So anyway, this is the formula for osmotic pressure. So again, osmotic pressure is just symbol is capital. This is the Greek letter P, so that's where pressure pi, and it equals mRT. Now M, remember, is molarity. So because you're not heating it up, the concentration can be in molarity. So M is the molarity, R is the ideal gas constant that we've used before, 0.0821 liters atmosphere mole Kelvin. And so T has to be in Kelvin so that it will cancel. So if you cancel, if you look at that, this is moles per liter, and this is liter, atmosphere, mole, Kelvin, and this is in Kelvin. So if you see what happens, let's use a different color. Kelvin will cancel, moles will cancel, liters will cancel, and notice that pi, which is that the pressure, will be in atmosphere. So your atmospheres will be your unit for pressure. You can convert it to other pressures, but it has to be in atmospheres when you're using this equation because R is in these specific units. So let's say we have a 1 molar solution of glucose. What will the osmotic pressure be? The osmotic pressure is the molarity, 1 mole per liter, times the R value, 0.0821, times the temperature in Kelvin, 298. So the osmotic pressure of a 1 molar glucose solution is 24.5 atmospheres. So that's pretty easy to calculate. You just have to know molarity and then plug it in. So like I said, why is that important? Because it's really important in our human body. So what happens if you have two solutions that have identical osmotic pressure? Now again, remember, osmotic pressure is colligative. It doesn't matter what those particles are. It could be sugar, it could be salt, it could be ethylene glycol, it could be benzene, it could be all kinds of things. It doesn't matter what it is, just what its concentration is, because the molarity. So you can have two solutions that are equal in osmotic pressure. What that means is their molarity is the same, their molarity of particles is the same. And in that case, if you have two solutions with a semi-permeable membrane in between, no osmosis will occur. So that's a good thing. These two solutions then are said to be isotonic to each other. If one solution has a lower osmotic pressure, then it is hypotonic with respect to the other. And if one solution has a higher osmotic pressure, it is hypertonic with respect to others. So again, what does this have to do with us? Well, it has to do with a cell, let's say a blood. So if we have, let's see what my picture is. All right, so let's say I have a cell, and here's a blood cell, so it's in my blood vein. And my cell has a particular osmotic pressure, and then my blood has a particular osmotic pressure. As long as the osmotic pressure are the same, my blood cell is happy. So because a cell is surrounded by a semi-permeable membrane, this is important. So solutions surrounding cells must be isotonic for the cell to survive. So if you so what if, like they say, don't drink salt water. What if you started drinking some salt water? You drank because you were stranded on an island and you were drinking a bunch of salt water. So all of a sudden, the osmotic pressure surrounding your cell increases. So osmotic pressure. So now it could just be that they give you too much salt in the hospital or something. So or you drink a lot of salt water. Anyway, what if the osmotic pressure in the blood goes up? What's going to happen because they're not isotonic to each other anymore? What's going to happen is the water is going to come out of the cell to try to dilute the liquid in the blood. Your cell's going to shrivel. It's literal. I know you've probably heard this. If you drink salt water, you dehydrate. Well, literally, your cells are giving away water, and so they are literally shriveling because they're losing water. So they are dehydrating, and that process is called crenation. So that's why you shouldn't drink lots of salt water, because you're going to dehydrate yourself. Literally, your cells, the water in your cells will move out. So what if instead, let's use a different color, what if instead you just, I don't know, let's say they gave you an insult, like you're in the hospital, and they give you pure water instead of a saline solution. So now the osmotic pressure of your solution around your cell decreases. What's going to happen is that the water is going to try to, now the inside the cell is more concentrated than outside the cell, water's going to flow into the cell, and in fact it may burst. The cell may burst. This is called hemolysis. And so what you want is you want your osmotic pressure of the solution, like your blood, for example, to be the same as your cell. And so I find it kind of interesting, but it's all, again, it's all a colligative property. Oh, here's a good picture. So, right, if it's less concentrated, then the water will flow into the cell and they will burst. If the concentration outside the cell is the same, if they're isotonic, then everything's fine. If you have if the concentration outside the cell is too high, too concentrated, then the water will flow out and you will have crenation. You'll shrivel. All right, so I find this really interesting. So the average osmotic pressure of blood is 7.7 atmospheres at 37 degrees Celsius, which is about body temperature. So what concentration of glucose, if someone wants to give you a glucose IV, what should the concentration be so that it's isotonic with blood? So remember that osmotic pressure, pi equals mRT. So we know R is a constant, T, we can find T because we know the temperature, and we know P, 7.7. So if we solve for molarity, molarity equals pi over RT. Pi is 7.7 atmospheres, R is 0.0821 liter atmosphere mole Kelvin, so the atmosphere cancel. Temperature is 310 Kelvin, so Kelvin cancels. And so the solution should be 0.3 molar. We want 0.3 molar glucose to be isotonic with blood. So that's pretty good. I will talk more in a little bit about, that's not, I can't remember, it's like a percentage. When you go in the hospital, your IV is like a 5% sugar solution, but we'll talk about that in a minute. It just all has to do with different concentration units. Okay, so anyway, osmotic pressure increases with concentration. Now, here's where it comes in to where I was talking about ionic solutions. So it gets kind of a little bit complicated and so we haven't done any examples with salt or any kind of salt. And that's because remember that colligative property only depends on the total concentration of the particles. It doesn't care what its identity is. It only wants to know, I mean, literally count the number of particles. The more concentrated it is, the more that colligative property is true. So it only cares about the particles. And so the important thing is when you have an ionic compound and it dissolves, it dissociates into more than one particle. For example, NaCl, when it's dissolved in water, will produce Na plus Cl negative. So if you have a 1 molar concentration of NaCl, you actually have 1 molar Na plus and 1 molar Cl negative. So actually your concentration is actually double what you think it is. So the actual concentration of particles is 2. So this is really important. So what we're going to do is we're going to alter our colligative property formulas to take this into account. So actually, I should have done this at the beginning, but they like to add it at the end. We have to have, so delta TF equals KFM times I. Delta TB equals KB times M times little I. Pi equals MRT times little I. And what is little I? Little I is how many particles does that compound break into when it dissolves. So I is just like the number of ions resulting from each formula unit. So we have to multiply. So like if it's NaCl, the pi will be twice as much because the total concentration of particles will be twice as much because it breaks into two pieces. So you have to know what that number is. If you see that a solute is non-dissociating, so that's why we've only used glucose or different, let's see, ethylene glycol or benzene. All of those so far have been non-dissociating, so I just equals 1. So if it's something that if you put it in water, the same number it stays the same number, then that's why all the problems so far that we've done have worked, because I equals 1, non-dissociating. So sometimes if they don't tell you what it is, but they say non-dissociating, you can know that little I equals 1. So let's do an extra problem. So let's find the freezing point of a 0.5 mol aqueous solution of aluminum sulfate. And we're going to assume that the value of I is based on the formula. So the first thing we want to do is, and this is why your polyatomic ions and knowing your ionic equations from first semester is really important. So what happens when aluminum sulfate dissolves? So again, now the sulfate doesn't dissolve into every little, they stay together. There's 3 sulfates and there's 2 aluminums. So it will dissolve into 5 ions, right? So if you need to go back and review your polyatomic ions, go back and review, it's probably chapter 4 in your book, where you need to be able to find out how this will dissociate, be able to pull it apart and write it as its ions. Now you don't have to do it, you just have to be able to know. So notice that there's 2 aluminums and 3 sulfates, so that's a total of 5 particles. So we assume I equals 5. All right, so now it's just a normal problem. So the freezing point depression is I times Kf times m. So I is 5. Since this is happening in water, it's aqueous. So Kf from that chart previously is 1.86. And they're telling us the molality of the solution is 0.5. So it's 0.5 times 1.6, but it's 5 times as great because there's 5 particles. So we have to multiply by that 5. So delta Tf is 4.7, which means that the freezing point is negative 4.7. So anyway, going forward from here, just remember that all your formulas should have little I attached. And if it's ionic, you need to figure out what I is. If it's not ionic, usually the problem will say something like, this is a non-dissociating particle or something like that, and then you know I equals 1. All right, so let's kind of work through this problem. Which of the following solutions will have the lowest freezing point? Well, remember that delta Tf equals I Kf m. Now notice that these are given the concentration of, we don't have to actually know what Kf is, and we could calculate delta T for all of them if we wanted to. We could look up Kf and we could multiply it, but there's a term, so if you take out the K, because K is going to be constant no matter what, as long as you're using the same solution. So if you just take the I times the m, this is called osmolality. Osmolality is a term. So osmolality equals little I times m. So in other words, it's what's the concentration of actual particles. If it happens to be molarity that you're talking about, then you can use osmolarity, which is I times m. So depending on if you're using little m or big M, it's osmolality or osmolarity. So what we can do is we can figure out the osmolality of each of these without worrying about the whole formula. So I, in this case, is 3 because this is going to break up into 2 plus 1, 3 particles. So 3 times 1 is 3.0 osmol. So the concentration of this solution is 3.1 osmol in terms of particles. This one KCl, I equals 2. It breaks up into 2 particles. So this one will be 2 times 2.0 or 4.0 osmol. This one, because it's non-electrolyte or non-dissociating, either one means the same thing, this means I equals 1. So in this case, we have 1 times 3.0 equals 3.0 osmol. So at first glance, you might say, well, of course this has the lowest freezing point because it's the most concentrated. But in fact, the KCl will have the lowest freezing point because it's the most concentrated of all because of the little I. And of course, the CONO32 is actually the same as this is ethylene glycol antifreeze. They're the same, even though this is 1 molar and this is 3 molar. That's because this breaks up into 3 particles. So in this case, the lowest freezing point is the KCl. So you want to remember little I. All right, yep. So there, I just went through that problem. KCl is the lowest freezing point. So osmotic pressure also depends on the number of solute particles. And so this is kind of a little aside as well. Remember that I said earlier the molarity of glucose at its isotonic with cells was found to be 0.3 molar. Glucose is non-dissociating, so little I equals 1. So that would also have an osmolarity of 0.3. Because it's B1 times 0.3 equals 0.3. But if it's saline, so if it's sodium chloride, the sodium chloride isotonic with blood then would be 0.15 molar because NaCl breaks apart into 2 particles. So if we had 0.15 molar times 2 particles will give me an osmolarity of 0.3. So we would need a concentration of NaCl that's half that of glucose, so that our osmolarity would be the same. So just keep that in mind too. And I just for an aside, in a clinical situation, concentrations in hospitals are usually expressed as a mass percent, and of course we know how to do that. So it turns out that glucose is a 5.4% and saline is 0.9. I think it's 0.88 or something. It rounds to 0.9. So just looking at it, like if you have a 0.3 molar times 180 grams per mole, let's see, moles cancel. So then now I have grams per liter. And then if I convert to milliliters, then I have a solution is 5.054 grams per milliliter. And then times 100, if you get it to percent, is 5.4% solution. Saline, interestingly, since saline should be 0.15 molar, it's since the molecular weight of saline is different, 58.4, and then again we convert liters to milliliters, we have 0.0088 grams per milliliter, which is a 0.88% or 0.9% solution. So interestingly, but notice that even though they're very different amounts, they all have the same osmolarity, which makes them all isotonic with each other. And of course, if you had some other solution, sodium carbonate, or I don't know what, calcium carbonate or calcium sulfate or something, you know, you would have to figure it out individually. Okay, so the very last thing that we're going to do is to determine the molar mass from colligative properties. So this is kind of an interesting idea in one of the labs that we do this semester. All of the 4 colligative properties can be used to find the molar mass of an unknown. And in fact, some proteins and some large molecules are actually, it's done this way so that you can, it's a good way of doing it. Finding out, like if you have a new molecule and you want to know what is its mass or what is its molecular weight, you can do it this way. So, for example, let's say we measure the freezing point. We know the freezing point of a pure solvent, And then we measure the freezing point depression. What is the freezing point of the solution? Then we can find delta TF. So we know the difference between them. Because delta T depends on the concentration, we can find out how many moles of the unknown are dissolved. And remember, molecular weight, or molar mass, molecular weight is grams per mole. How many grams are there per mole? So if you can find the delta TF, and remember delta TF equals IKF times M. Since we know what KF is, and generally speaking, you'll have to know what I is. For the most part, we're going to only use non-dissociating. So most of the time, I will just equal 1. And at least as far as what we're gonna do in this class. So most of the time, I will just equal 1, so we can ignore it. KF is given to us, so then we can find the concentration of the solvent. Now, in the problems what we've done so far, we knew how much of the solvent or solute we put in there, and we could calculate it because we knew the molecular weight. What we're going to do is back up and do it differently. We're going to find out how many moles we have, and we're going to have to put a certain amount of grams. We're going to measure how much we put in solution, and then we'll be able to calculate the molecular weight because we will know the total number of grams we put in, and we'll be able to calculate how many moles that's equivalent to, and so we'll be able to find molar mass, molecular weight. All right, so let's look at an example, and we are doing one of these in lab. So either you're watching this after we've done it or beforehand, then you know we're going to be doing it. So let's say we have, so non-volatile, so again, we don't have to worry about it boiling or anything, so that's good. And it's a non-electrolyte, so what that tells us is that I equals 1, so we don't have to worry about little I. So a solution was prepared by dissolving 0.25 grams, so that's my mass, of the substance is unknown. So we can't figure out how many moles it is because we don't know what it is. We don't know its molecular weight, but we know it's what we're looking for. And we've put it into 40 grams of the solvent, carbon tetrachloride. The boiling point of the solution was found to be 0.357 degrees higher than pure carbon tetrachloride. So they're telling us delta TB equals 0.3. They didn't tell us what the actual boiling points were, what carbon tetrachloride is, and what the actual boiling point of the solution was, but they told us the difference between them. So delta TB. Sometimes they might give you the initial boiling point of the pure solvent and then the final boiling point of the solution, and then you have to figure out TB. But in this case, they're telling you what it is. And so what we want to know is what is the molar mass of our unknown? And they're telling you what Kb is. All right, so we know our formula, TB equals I times Kb times M. We know what Kb is and we know what I is, and we actually know what Tb is. So now we're going to rearrange this equation and we're going to solve for M. So M equals delta TB, which is 0.357, divided by I, which is 1, divided by K, which is given to us 5.02. So the molality of our solution is 0.0711 moles, and molal, so remember molal is moles of solute per kilogram of solvent. So again, let me just draw a little picture here. We've put 40 grams of carbon tetrachloride, and then we've added 0.250 grams of our unknown. And then we took the boiling point of that solution. So just keep that in mind. So anyway, like I said, we put this 0.25 grams of unknown and 40 grams of carbon tetrachloride. So what we're finding out here is that our concentration is 0.0711 moles per kilogram. Now that's still not, we still don't know what it is, but we can figure that out. So the next step is what we want to do. Remember, let me come over here. Remember that to find molar mass, we have to find moles, grams. Let's erase that. We want grams per mole. Molecular weight or molar mass is how many grams equal how many moles. How many grams per 1 mole, or in other words, how many grams divided by how many moles. Well, we know the grams. It's equal to 0.250 grams. So if we're able to find the moles, we can plug that in and find molecular weight. We don't quite know the moles yet. We know how many moles we have per kilogram, but notice that we don't have a kilogram of solvent. We only have 40 grams of solvent. So we have to do one more calculation to find out how many moles of solute we have. We have to take into account this 40 grams of solvent. So that's the next thing. So we have to multiply the concentration by the weight of the solvent in kilograms. So if we knew it was 0.0711 moles per 1 kilogram, if we multiply by 0.040 kilograms, it's 0.00284 moles of unknown. Or another way to think about it is it's 0.0711 moles per 1 kilogram. So how many moles are in 0.040 kilograms? 40 grams or 0.040 kilograms. So that's really the same thing. You could do it this way and you could solve for X. So we know our ratio is 0.0711 per kilogram, but we don't have a kilogram. We only have 0.04 kilograms. So what is X? X is 0.00284 moles of unknown. So now, like I said earlier, we can find the molar mass because it's just the grams, 0.250, divided by the moles, which we just calculated. And so this turns out that our unknown is 88 grams per mole. So that's probably going to be a question like this on the test. You could do this with any of the colligative properties. So this one was boiling point. You could do it with freezing point, which is the one we're doing in lab. You could also do it with osmotic pressure, which I think is the next example. All right, so using osmotic pressure. So an aqueous solution was made by dissolving 3.5 milligrams. So remember that's 0.0035 grams, just for your information. Divide by 1,000. 0.0035 grams, 3.5 milligrams of a protein in enough water to give us 5 milliliters of solution. So that's the volume. 5 milliliters of solution is water. The osmotic pressure of this was found to be 1.54 torr at 25 degrees. That's important because the formula uses the temperature. So calculate the molar mass of the unknown. Keep in mind that a protein is non-dissociating, so I equals 1. So we don't have to worry about that. So remember our osmotic pressure formula. Pi equals I mRT. And of course, I is just 1, so we can ignore it. Similar to what we did before, we know the osmotic pressure. We know the R, because that's just a constant, and we know the T. Make sure and put it in Kelvin. And we can solve for molarity. Now, we have to be careful because remember, if we're using R is in terms of atmosphere. So the first thing we have to do is convert our pressure to atmospheres to be able to work this problem. So we have to convert 1.5 torr to atmosphere, so 0.00197 atmospheres. So that is what pi is. And our Kelvin, 25 plus 273 is 298. So now we can solve for molarity. So molarity equals pi, 0.00197, divided by I, which is 1, divided by R, divided by T. And so we get 8.28 times 10 to the minus 5th molar. Remember, molar is moles per liter. Again, what are we trying to find? We're trying to find molecular weight. Molecular weight is grams per mole. So we know the grams because that's up here, grams. And we want to find the moles. right now we know how many moles there are per liter, but we want to find out how many absolute moles there are. So we're going to have to multiply by the volume. So 8.28 times 10 to the minus 5th moles per liter multiplied by the total number of liters that we have, which is 5 milliliters or 0.005 liters. Remember, this is similar, 8.28 times 10 to the minus 5 mole per liter. But we want to know how many moles are equal to 5 milliliters, which is 0.005 liters. So 5 milliliters. So this is your ratio. So we're trying to find out what X is. So you multiply your concentration times the volume. Gives you moles. So that's how many moles we had. I know that looks like a very small number, and it is. And now we can find molar mass. Molar mass is grams. 0.0035 grams divided by moles gives us 8.45 times 10 to the third grams per mole. So what is that? 8,450 grams per mole. That's a really big molecule, but remember it's a protein, so proteins are very large. So that's often how they can find the molecular weight of very large molecules. We're using osmotic pressure. Also polymers, other kinds of macromolecules can be done this way. Anyway, that is the chapter. What should you be able to do at the end of this chapter? You should be able to explain the solution process, why some compounds dissolve and others don't. Be able to apply Henry's law, which says that the concentration of a gas in a liquid increases with increasing vapor pressure. Be able to calculate solution concentration, and that could be in terms of molality, mole fraction, molarity, and percent composition. Be able to convert from one unit of concentration to another unit of concentration. Be able to calculate vapor pressure lowering. Be able to calculate the boiling point elevation and freezing point depression. Be able to calculate osmotic pressure. Make sure to include colligative properties of ionic solutions, so be able to find out what little I is in terms of ionic solutions, and then be able to calculate molar mass using one of the colligative properties.